Okay, so last time we had our introduction to some degree, and we talked about how to just represent information in a more presentable way. By way of a frequency table, the information is a little more structured, and it's easier to convey what the information is telling us and to just read off what the information is telling us by way of a frequency table, as well as the graphical version called a histogram. So it's the same information, whether it's summarized in a table or graphically with little bars. The information is much more presentable. Now we want to move on to chapter 2, where I want to have a number that represents the information, sort of in a summarized way. It'll probably be a couple of numbers representing different aspects of the information, sort of as a summary, as a key property of the information. In addition to this histogram or frequency table, so let's go to my slides 2. Again. So if I look at the stress rating example, the first thing I want to look at is the average rating. And by average, I mean the one that we intuitively understand to be the average, where I'm going to add up all the numbers and I'm going to divide them by how many there are. So a way to represent that calculation is, this is a capital sigma representing the sum of all the scores that I represent by an x. So if I add up all these numbers, a little tedious, but I'll get 193. If I count how many there are, we'll represent that by an n, 30 of them in this case. So we take the average by adding them up, getting 193, and dividing by 30. So the average stress rating in this example was 6.43. So we can use that average to describe sort of the typical value that sort of balances between higher values and lower values. What is the average stress rating that I got? Graphically, what I can see it as, if I look at the histogram, it's in a sense I can visualize it as the balance point, where if I have a little triangle and I rest this whole thing on top of that, everything's exactly balanced. It's the average. Another way of seeing it is, if I take many people's scores, stress rating scores, in the long run, I'll average here around 6.5. Sometimes someone will get a high stress rating, sometimes someone will get a low one. But on average, it'll balance out, and the sort of the center value, the middle value that occurs most often, is somewhere in the 6.5 range. So that is what we call the average, or the mean. So mean is just another word for average. You can use either one really, but when you look at the book, they'll use the word mean. So that's the first one, sort of giving me an idea of where the center of the distribution, the frequency distribution, sits. Where's the most common value by looking at an average? So we have to get used to this sort of symbolic way of representing the calculation. Just to be able to read the fancier ones and be able to sort of express how we calculate something like this. The sum of all the x values, all the scores, divided by the total number. And we'll call that the mean. Everyone happy with the symbols? Okay. Then, if I look at another example, the living country example where we asked for a set of 110 people, how much do you like to live in the country or not at all? And these were the results. If I look at the mean, the average, I add them all up, and I get 401. I'm going to look at the bottom right now. I add them all up, and I divide by how many there are, just the average that everyone is used to. I think if you ask anyone out there, oh, how do you calculate the average of some numbers, they'll tell you, add them up and divide them by how many there are. So I get sort of the balance point, sort of the center of the distribution at 3.65. So it's a little under the middle score, but it's fairly well positioned in the center. If I look at another example, just getting used to the average, the mean, the horn honking example, where I measured the time it took for someone to honk at the person in front of them not moving, and I had these 29 values, add them up and divide by how many there are, and I got an average of 2.84 seconds. Sort of in the middle of the range of values from 0, this person was very aggressive, to 5 seconds seemed to be the largest one. Something sort of in the middle, the average value. There are other ways to talk about the center of the distribution. The mean is by far the most common one. But there are others. We can look at the mode, and that is the most frequent value that occurs. So when I look at my frequency table, I simply pick the one that occurs the most often. So in this case, the mode is 3.5. In this sample, this collection of scores that I have, 3.5 occurs most often. So it's another way of highlighting the property of the distribution, sort of where is the center, where is the most common value. The mode isn't used as much as the mean, but it's just good to be aware of it. When I don't have a lot of values, the mode can be relevant for many common distributions, or one of the main ones we'll be looking at. These are often the same or close to the same. Yeah.
Let's say if the mode had been 5 seconds, would you still say that that's the center?
Personally, in general, no. In general, the mean and the one we'll do next is the most common one. But it's good to be aware. Sometimes my collection of numbers are a little strange, and it's just good to be aware of what does the mode say. Does it agree? Is it drastically different, and why?
Okay.
If it's drastically different, which one makes more sense to use?
Okay.
But in general, the mean is the one I'll go to first.
Okay.
So it's just good to be aware. Sometimes I get weird things. As we'll see in a second, maybe there are more extreme values that I don't get often, but in my collection I happen to have them. Then the mean values are affected by that, whereas it's not really common. So I want to just be aware of other options to describe the center of the the data that I would get in general.
Okay.
But the mean is the first one, for sure, and by far the most common in general. Yes.
When we were talking about like unimodal and bimodal
Yes.
yesterday,
That was the mode, yeah.
That's
So it could happen in the frequencies. This is a nice setup example. It could happen that 1 second occurs with a 6 as well. And then I have a bimodal distribution based on this. So then you can't really talk about, according to the mode, a single central value. There's sort of two, depending on what happened. Like the ages in the toddler play area, there were 2. So what's really the center value? The main common value? Well, there would be 2 because of the 2 separate age groups. So it depends, In general, I have to look at what I have and see, does the mean seem appropriate? If not, there are other options. The mode is one, but the median is the other one. So in terms of common usage, by far, it's sort of ranked mean first, mode would be last, the median is sort of in the middle. A little more useful. What is the median? The median is simply when I rank all my scores from, let's say, smallest to highest, and I look at what is the value that sits in the middle of that list. So the smallest value I get is a 0, the highest value I get is a 5, I put them in order, and I have 29 values. So the value that sits in the middle is number 15. 14 above it, 14 below it, 1 in the middle. That's called the median. The actual center value. Regardless of what the scores are, the one that sits halfway in the list, that's called the median.
So would it be accurate to say that that's actually a measure of the position?
I have to look at the center position when I rank them. Yeah. So in this case, it's a 3, and in general, it depends on the distribution. For a nice balanced symmetrical distribution, the mean and the median will be similar, if not exactly the same. So I have these 3 that I just want to be aware of. The mean is definitely the one we'll use more often, far more often. Then, depending on what kind of values I observe, the median is a good one to compare, and the mode as well, if I want a third option. So, in terms of finding the median, it's a little bit more tedious because I have to rank them. But software packages will do that ranking for me. Or I'll have a small manageable list of numbers, so it's easier to do. As soon as the set of numbers become large, then I have to do something more automated. So if I have an odd number of scores, like 29, how do I determine which position is the middle position? Oh, their example is 15, our example is 29. I would simply take the total number plus 1 divided by 2 to get 15. So if I have 29 scores, I add 1, which is 30, divided by 2, and it gives me the number 15. And I can intuitively, I can verify that 15 is the middle, because I need to have 29. So it's halfway between, it's halfway in the list, because I have 14 above it, 14 below it, give me 28, and the center value is the 29 value. Whereas if I have, so I just want to verify, I think there are some typos here. If you have 15 values, 15 plus 1 is 16, divided by 2 is 8. The 8th number is the one in the middle, not the 7th number. I don't know where that typo comes from. This should be an 8. Because it separates it into 7 below, 7 above, and the middle value. So that's a little typo. It should be an 8. When I have an even number, then technically there are two scores in the middle. There isn't a single middle value. If I have an even number, like 16, if I have 16 values, then it's split into 8 and 8, and there's no center value. The center is a gap between two values, the 8th and the 9th value. Again, I don't know where this typo comes from, 8 and 9, not 7 and 8. 8 and 9. So you just take the 16 divided by 2, and it gives you an 8. But because it's an even number, it's going to be split into two equal halves of the list. So then I would simply take the average of those two middle scores. So let's just suppose I had another one here, giving me 30 in total. Then both of these guys would be the middle value, so to speak. The middle would be right in between them. So I would average out those two values, but because they're the same, I still get a median of 3. So it depends, the calculation is slightly different if it's an even number of scores or an odd number of scores. If it's an odd number of scores, then I have a middle value, and that value is the median. If I have an even number of scores, then I have two values sitting in the middle, and I just average them out. Often they're the same, like this example, if I add another one, but the calculation is slightly different. Does that make sense for the median? I'm looking for the middle value, and if there happens to be 2 in the middle, I just average them out. All right, let's see. The median has two places where it might be useful. When I have a rank order variable, then it's often useful to consider the median. And also if I have extreme values in my collection. I think 2.4 would show something like that. So let's just look at the first example, where I just have some scores that come from wherever. And I have a bunch of low scores and a bunch of high scores. And then one in the middle. The average is going to look at all of them and give me the average, which would be 5.27. The median would simply rank them and look at the center value, which is A. So if I have sort of extreme values on either side, the median and the mean could differ quite a bit. This example, I have some low values and then some extremely high values. The median and the mean would be very different, depending on what's a common value. Maybe these are common values. Maybe the 50 won't come up often. The mean is pulled in the higher direction because of all these 50s, whereas the median just looks at the list and picks the center value. So it's not affected by those 50s or these 7s as much as the mean is. So often if I have a list, if I have a set of scores, if I go back to my horn honking example, let's suppose I'm gathering some information for different people. I have these values that seem to be not too extreme. And let's suppose I get someone that took a really long time. I guess they fell asleep or something. They took like 10 seconds before they responded. That's sort of an extreme value. That doesn't happen often at all. The mean would be affected by that extreme value. If I put it 10 seconds here, the mean would be pulled up quite a bit. Whereas the median wouldn't care at all. Because if I rank them, the bottom value would be a 10, but the median is still the middle value. It's still around the 3s, so it's not affected by those extreme values as much. So I have to look at my collection of scores, see, is there anything that's sort of extreme, we call it an outlier, that doesn't happen often, then the median is worth considering because it's not going to react to an observation that's sort of not common at all. So it's good to keep these guys in mind, but for the most general purposes, the mean is the one that I go to. It's a formula, it's easy to calculate. It's definitely the most common one. I'll always do the mean. But then if you see something strange in your sample of score values, then it's worth keeping in mind. Well, what does the median say? How does it compare? Maybe they're the same. Then it's just a better indication of where the center of your data set sits. If I go to 2.6, the skewness of the distribution is linked to how the mean, median, and mode sit in relation to each other. If I look at the first one, is that a positive or a negative skew? Negative? However you want to remember it. His way to remember it was, I have to move it in the negative direction to get its center. So negative skew. But everyone has their own way. I think of the tail being in the negative, on the negative side, negative skew. And then the mean will be smaller than the median, which is smaller than the mode. The mode is the peak value. If I have a positive skew, then it's the reverse situation. So by just looking at the three numbers give me, each one gives me the central location of the distribution, but in a slightly different way. And if I combine the three, then I have even more information. And if I look at a nice and balanced distribution, then they are all the same or very close to being the same. So by just comparing those three values, I can say something about how the distribution is skewed or off-center as well. All right. That is the end of the first part. Any questions about the or indicating or measuring the center of the distribution? Any questions? All right. There is something else which, I just want to see which slide I'm looking at here. If I look at this one, if I look at an example like this, like the living country example, the mean is a good indication, is a good measure of what the distribution, of a property of the distribution, but it's not the only important property that I want to highlight. The other issue that I have is if I look at the mean, 3.65, it's somewhere in the middle, it tells me what the average result is, the average score, but it doesn't tell me what I can really expect. If I surveyed another person, do I expect that person's score to be close to this average value? Or does it fluctuate a lot, but in the end it averages out to be around 3.5? There's another property called the variability of the distribution, which is important to be aware of. How much fluctuation is there in the results that I get? Do they all sit around here, 3, 4, 5, 4, 3, 4? They're packed very closely around the mean. Or do I get extreme values? Are the opinions going to fluctuate a lot? Many people say not at all. Many people say, yeah, I want to live in the country very much. But they still average out to 3.65. Those are two very different distributions. So I have to look at something called the variation. How much does it vary around the mean? And those two in combination really tell me what the distribution is. What can I expect? How does this variable behave in terms of the scores that people get. So let's look at 2.7. So on the right, let's look at the B column first. There I have a similar shape to the distribution. It has a couple of little peaks and it's sort of spread out in the same way. But the mean tells me sort of where the center position is. If I average out all the scores, this first one has a 1.7 average. This one has a 3.2, so it's obviously different. This one has a 2.5 average. And how much variability there is seems to just visually be similar. They're sort of the same spread around the mean. But if I look at these guys with all the same mean, they're not necessarily the same distribution just because they have the same mean. They're spread around the mean in different ways. This one is nice and centered around the mean, which if I can measure that and describe that property, then I know what to expect. If I get scores according to this distribution, then I know they're just going to deviate a little bit around the mean, not too much. And it's nice and symmetric as well. This one, I get values that are further away from the mean more often. And this one, I get values that seem to be on that side of the mean more often, and values spread out more on the left, still averaging out to 3.2, but the spread around the mean is different. So it's a key property of describing the distribution, not just the central location, but how the values are spread around the mean. How much fluctuation, how much variability can I expect? All right, let's go to 2.2. Now, how do I come up with a calculation to give me a number to represent that variability in a similar way to the number that represents the central location by way of the mean? So it's a more complicated thing to describe, so the calculation is going to be a little more complicated, but really not that bad once you get the hang of it. So, let me think. So if I look at the following calculations. So I have my 110 people here that were surveyed. If I look at them one at a time, so the first person's score was 7. That person definitely wanted to live in the country. I had very strong feelings towards that. So person number 1 had a rating of 7, a score of 7. If I compare that to the mean, to the average, 3.65, I want to now keep track of the difference between the actual score and the average score, the deviation, so to speak. So if I take the average, if I take the score of that person, 7, and I take away the mean, that's the distance between the two, the difference between the two, 3.35. Don't worry about the last column just yet. The second person had a score of 5. It's not as far from the mean. It's only 1.35 away. The next person had a score of 1. They did not want to live in the country at all. How far is that away from the mean? Well, now it's on the other side of the mean. The mean sits over here. If it's over there, the score, then it's a positive difference. If it's over here, then it's a negative difference. So I get a negative 2.65. Just indicating where the actual score sits in relation to the mean. Sometimes I'll get a positive value. The bigger ones indicate that the actual score is further away from the mean. Smaller values meaning it's not that far away. Negative deviation values mean that it's still a distance away, but on the other side. So I want to essentially take all these deviation values and average them out. Take all the differences between the actual scores and the mean value and average them out to give me an idea of the average deviation. But the problem is that if I do that, the positive and negative numbers will cancel each other out. And I'll get a false impression of how much deviation there actually is. If I add this, I get, I take 3.5, 1.5, so that's just under 5, and then I add a negative 2.6, it's going to lower the deviation. So the positive and negative numbers will cancel each other out if I use this column. And it might not give me a good representation. It might seem to be smaller than it actually is. So one way to fix that is to square these numbers. So 3.35 squared is 11.22. 1.35 squared is 1.82. Negative 2.65 squared is positive 7.02. So by taking the square of those numbers, I make them all positive. And the bigger deviations will still have bigger values in this last column. So the relative size of the deviations are still captured. If I then add up all of these, they're all positive. They're all contributing. Any bit of deviation adds to that sum. We call that the sum of the squares, SS. 347.18 when I add up all those values. And then I'm going to take the average of that. Take the average of that. And I'll call that the variance. So I'm keeping it low because I don't want to reveal too much. So in the symbolic notation, so to speak, I take the sum, add up all the differences between the actual score and the mean square, so that negative and positive values don't cancel out. I use the square. And then I just take the average, divide by how many there are. So I get the sum of the squares is 347.18. There are 110 of them. So I get an average of 3.16. And I can't really interpret that very well. It's just a number associated with how much deviation, how much fluctuation, how much variability there is in my scores. The problem is that these numbers are squared. So this guy is not the same as a rating value because I squared it. And if I'm talking about the height of people, for example, then if I measure the actual scores in inches, then the deviation values will still be in inches, but if I square them, now it's inches squared. It's hard to understand what this number means because I squared everything. It's a little weird. So I just take the square root of that to get it back to a number that I can compare with my actual score values. The bigger the variance is, the bigger the square root of the variance is going to be. And we call this square root guy the standard deviation. So the standard deviation is the standard way of looking at variability. It gives me a number that I can say, okay, the bigger this one is, the bigger the standard deviation is, the more variety I'll see. Up and above the mean, below the mean, it fluctuates much more than if it had a low standard deviation. So it's a measure, so the mean was a measure of the location. Where is the center? Where's the balance point of the distribution? The standard deviation tells me how things are spread around the mean. A high standard deviation, and I get values on either side. It fluctuates much more. A small standard deviation, and everything is just sitting around the mean. There isn't much fluctuation. So both the central location and the variability in combination, we need them both to be able to say how the distribution behaves. These two are key building blocks in everything we'll do. What slide is this? 2.2. So let's review how to calculate that by looking at 2.8. Calculate the variance. Once I have the variance, the standard deviation is just the square root. That's why the symbol is standard deviation squared. The standard deviation is one I can more easily talk about, but it comes from the variance. I have to take the variance root to actually calculate it. So I take for each score, I calculate the mean, and then I go one score at a time. What's the difference? What's the deviation? Then I square all of them to make everything positive. Add up, take the average of all those squared deviations, and that gives me my variance. And then I simply take the square root to get the standard deviation. It's not here. Simply take the square root of that to get the standard deviation. Now, if I have bigger samples of scores, then I would have to automate this and let the computer handle that calculation. But it's still good to just do with small sets. It's good to just do it by hand a few times, because then it sinks in how it's calculated. And as soon as I get something bigger, we'll see how SPSS can do that. Any questions on the calculation? So the mean on its own is not enough to really describe the distribution accurately. It gives me the position of the central location of the distribution, but how things are spread around it is also important, and that's what the standard deviation or variance captures. Let's do, we did 2.2, let's do 2.5, the Horn-Hawking example. So in this case, it's nice and balanced. If I look at the mean, oh, there was one thing here that compares the mean and the median again. If I look at my Horn-Hawking example, do I have the actual numbers? Oh, there it is. Horn-Hawking example. I took some times. Like I said before, if I add an extreme value, the one I had here was actually 13 seconds, not 10. If I add a 13-second result, 13 seconds, then the mean changes quite a bit, but the median stays the same. But they're both sort of in the range of the 3, so they agree fairly well. But that's not enough to really say, do people honk drastically less or more than this average? Is there a lot of variability in what I would see out there among people? Or are people pretty consistent around the 3-second mark? It's a key property of the distribution. So I would take each of the scores. I have two different cases. One where I have the original and one where I added the 13, just to see what happens if I have some extreme value in my data set. So if I take the actual scores compared to the mean, get the deviation values, and then take the square, the sum of the squares, and then I take the average of all these squared deviations. I get a variance of 1.38, 4.66. If I take the standard deviation, just take the square root so I can interpret it a little bit better. I get these two, I get 1.17 and 2.16. Does that make sense, that the right-hand side one is more than the left-hand side one? I just added that 13, but that 13 affects the distribution and the information, the property. That now with that 13, there seems to be much more variety, variation in what I can observe, because that one person that reacted so slowly creates more deviation. When I average it out, this 9.82 pulls it a little bit higher. Not too much. Actually, it's not nothing. It's quite a bit. It's almost double. Almost double. So the standard deviation measuring variability and spread around the mean will be affected by those extreme values, because those extreme values indicate that I get things more wildly spread around the mean, up or down. So both the mean and the standard deviation are sensitive to extreme values or outliers. So it's important that my sample of values sort of be a good representation of what people actually do. I might not have people in general waiting 13 seconds before they honk. So with that 13 seconds, it might not be representative of what people actually do, but the distribution will be affected by, or the measure of the variability will be affected by all the numbers that I see in my scores. Any question on calculating the standard deviation? So as long as we are aware of how to calculate it, we're not going to have too many values, and why we need both. Why we need both. They're saying different things about the distribution, and both of them are saying important things. All right. So depending on books that you look at in the future, there are other formulas to calculate these guys that might make the actual hand computations easier. But we're going to avoid them on purpose, because you're not going to actually calculate these by hand for very long. We're only doing it to sort of emphasize the idea. And then when you go to a computer, it doesn't matter what the formula is that we use. So we're going to use the sort of definition formula to calculate these, even though it's a little more tedious to do by hand. It shows the calculation much better, and it helps me remember it much better. When we have larger data sets, then I let the computer figure it out. But it's important for me to know the basics of how that number is calculated. Yes?
Speaking of different calculations, what would the benefit be of using n-1?
Right now I'm avoiding that whole issue. But in truth, what we're doing is we survey some people, and we want that information that comes from that little sample of people, we want that to be representative of the whole population. And it turns out that if I take my little sample and I calculate the standard deviation, for that to be an accurate estimate of the standard deviation of the whole population, you have to divide by n-1. And there's some math involved to prove that n puts me just off the actual standard deviation if I use an n. For now, I'm just getting used to the calculation, the idea, so we're not getting caught up in that. It's called an unbiased estimator. To be, let's say, an accurate estimator of the whole population, you need an n-1. But I'm doing it on purpose. I don't want to do it right now because people get caught up and focus on this instead of just the general idea. But yeah, it turns out that if you want to use your sample to make conclusions about the bigger population, if you use an n, it's going to be just off, just a little bit off. And the steps to prove that's a little mathy and tedious, to show that an n-1 points to the actual standard deviation of the population. But for now, we're just getting used to the idea. So it feels more intuitive to use an n here, showing that I'm taking the average, which I am doing regardless. It's just a matter of accuracy in general. But when we get to the inferential statistics, where we're taking a sample and drawing conclusions, or making conclusions from the sample about my larger population, then yes, we have to adjust that a little bit.